Right. So without losing much time, let's begin with the first what actually this course is about. So let me first share you or discuss about the handout. Okay, and then we will start with the course, the first lecture. Right. Okay. So let me start with the handout, sharing the handout on the slides. Okay. One second. Sorry, my computer is going very slow. Right. Right. I hope my screen is visible to you. And okay. So the course is microprocessor programming and interfacing. So myself, Chalapati. So I'm an assistant professor in the EEE department of Pilani campus. So we will have different tutorial sections beginning from the next Monday. We will have regular sessions in the tutorials next every Monday, first hour, and 1 hour of 1 hour on the Tuesday. I think there's one section which is not on Monday. And okay, so what is the course all about? Okay, the course is about a basic introduction to a processor. So you have been hearing of what is a processor and all those things in your general term, dealing with the computer and all those things. You say Intel Core 5, i5, i9 now, and all those things. But what actually is a processor? What does it actually contain? What is it capable of doing? Okay, so you'll be seeing little more closely in this particular course. Okay, so it will basically introduce to your processor the ISA. We will be dealing with the ISA level, that is instruction set architecture level, and we will be discussing about the assembly programming of the Intel 8086 processor. Okay, and then we will also be talking about the programmer's model of this processor. So how do you actually use the programmer's model, or how do we actually program a processor to do a particular function that we want to have? What does the architecture of the processor is made up of? What is its architecture? What are the different constituents of a processor? And then we will be dealing a good amount of lecture on the instruction set of 8086 processor, which is the processor that we'll be dealing. Okay, and we'll be talking about different modular assembly programming routines like subroutines, macros, etc. And we'll also talk about how actually the processor will execute a particular instruction. Okay, so we'll be talking with respect to the timing diagrams, what happens in a given time. Okay, and we will also have some concepts called hardware and software interrupts and all those things, right? And we will also talk about the memory as such. Okay, so memory interfacing, how do you interface the memory to the processor? Okay, and we will also talk about how you do the IO interfacing using different devices like programmable peripheral devices. And you will know what you will also we will also talk about DMA, direct memory access controllers. And we will basically, using all these components, at the end we will talk about integrating a processor based design, right? So we'll be talking about all these things, right? And the textbook for this is Barry Bray, the Intel microprocessor, by Pearson, 8th edition. That is what is will be our book that we'll be following. We'll also have a reference book, which is also a very good book, Douglas V. Hall, Microprocessor and Interfacing. That's the title by TMH, the second edition. Okay, so we'll start off with the computer architecture, memory, and I/O interfacing, and CISC and RISC processors first, and the other aspects which I have already talked about. Right. Okay. So what about the evaluation components, which generally, as a student, you will be seeing very interested about. Okay, so we'll be having a mid-semester test, which will be a 90-mark test, which will be in March 2021. So the date will be announced by the AUGSD at a relevant point of time. The comprehensive will also be on 5th May 2021. That will be for 120 marks, 40% of the course, and 35% of the course, 105 marks, will be for the mid-semester test. The labs, okay, will constitute a very significant portion, which is the rest of the 25% of the course. Okay, so what does the lab consist of, or lab aspect consist of? Okay, so we will be having around 8 sessions in the lab sessions. Okay, and we will also have 2 lab tests. Okay, so the labs are evaluative, so don't miss any of the labs. Okay, and don't rely on any buffers. We may not be able to give you any buffer. Okay, I repeat, we may not be able to give you any buffer, so please do not rely on any of the buffers. Right. Okay, so it is assumed that you will be attending all the labs. Okay, the labs will also be evaluative in nature. Apart from that, we will be having a lab test. Okay, we plan to have 2 lab tests. Of course, the thing will be announced by the IC at a relevant point of time. So we plan, as of now, as on today, we plan to have 2 lab tests, which will be, of course, evaluative in nature. Right. So both the regular lab sessions as well as the lab test will be evaluative. Okay, so total there will be of 300 marks, that is 100% of the weightage. Okay, so regarding the chamber consultation hour, or you can say office hour, or whatever you can say, there's no chamber now in the offline mode. Okay, so I plan to have it on Thursday, 5 o'clock. Okay, so I'll share you a relevant link where you can actually contact me for any doubt clarification, etc. However, you are free to, at any point of time, if you are not free at that time, or you want to have it at a different time, you can always drop in a mail to me or the IC, and set up an appointment, and we can discuss any questions that you have, doubts that you want to clarify. Okay, so the makeup will be granted only on very genuine cases. There's no makeup for the lab, as I told you. Okay, so don't think that you have a buffer for the lab. Okay, you are expected to be there in all the labs. There is no buffer for the lab. That is what you can assume. Okay, so if a student scores less than 20% of the marks in the course, he will be awarded an NC. Okay, so the displays of all the notices will be on Nalanda or through the email. We'll use Nalanda as the default notice board option. Right. Okay, so I have some pings on the chat box. So let me see what are if there are any queries. Right. The recording is on. We have already told this, right? Okay, so let's go to the lecture to start with. Okay. So what does we are talking about the microprocessor? What does the microprocessor talk about, or what is a microprocessor? Okay, so delving deep. Okay, so computing, okay, is not. Before that, let me talk about a little bit about the history before I actually get into the microprocessors. Okay, so uh, computing is not something very new to us. Okay, so though we have the first generation computing called as the ENIAC, electronic numerical integrator and computer. Okay, so which is told as the first way or first computer that you have. Okay, but computing is a very old and very you can say innate aspect of human. Okay, so even before we say that we have actually evolved or improved our computing of late from many century or sorry past few decades, especially after the World War II. However, computing of different forms have been already existing in the human society from time immemorial, even before abacus that you would have heard about. Okay, so computing is very, very, you know, uh, you can say, advanced way in an advanced way present in the human society. Okay, you'll be actually baffled, or you might be even surprised to know that the in the computing capabilities of the human society was very, very intense, especially in the Vedic history. If you look at it, there were a lot of prophecies or a lot of things that were made in the Vedic societies. For example, the way they are able to calculate the eclipses. Okay, by a person sitting in one place in the universe or one place in the planet. Okay, he can tell when a solar or a lunar eclipse will occur, maybe a few hundred years down the lane also. And they were very, very accurate in their computations. Okay. So, and you also have the way in which people used to calculate the trajectory of the planets. Okay. How different planets were placed and when they will be placed in a different way. Okay. They were all able to calculate with few calculations. Okay, on in sitting in one place in the world. So it was a very evolved way of computing, and it's not that as people generally say that they show a picture like this and say that man has started from an ape and all those things. So which is not true as per my understanding and my evidence. There's also a lot of evidence for this. Okay, so there's nothing like this. So people even few thousands and lakhs of years back also they were very, very advanced, and they had very advanced capabilities in terms of computation. Okay, in terms of the modern computations, it started with ENIAC. It was mainly for the trajectory tables for the weapons during the World War II, but it started in 1943, but it ended only 1946, First World War II. But it was used till 1955. It was a very, very big computer. I'll not touch a lot about this. It had 18,000 vacuum tubes, and it consumed a lot of power, 140 kilowatts of power. Okay, which is tremendous. Okay, it is something like you have, I think, 70 room heaters in a single room. Okay, something like that. That much amount of power was consumed. Okay, so it performed only 5,000 additions per second, and it was mainly doing some decimal additions, decimal computations, and it had 20 accumulators of 10 digits and all those things, and they were programmed manually by switches. Okay, so this is how ENIAC looked like. It's a very huge computer, and if a single mistake means you have to actually check in 19,000 possibility of which vacuum tube or which tube was to be replaced. So that's what ENIAC was. And then the second, after that, we started with the von Neumann computer. Okay, so it used a main memory for programming both the storing the both the programs as well as the data. So, and it was used in ALU for operating the on the binary data. Here we started with the binary data. Okay, so ENIAC used to work with decimal. Now this worked with binary data. So there was a control unit for interpreting the instructions from the memory and executing them. And it also had a input and output equipment which can be operated by the control unit. Okay, so basically it looked like this. You had an ALU, arithmetic logic unit, which used to take input from the from input device. Okay, do a compute control unit which control the memory as well as the ALU, and it used to do some computation and give back and put store that particular thing on the result of the computation on the output device. Okay, so the accumulator performed that operations of some computation. Okay, so it mainly had, as I said, five components: input component, output unit, input unit, and the control unit. And the ALU was the central part of this architecture. Okay, which interacted with the input unit as well as the output unit. It controlled the control unit to do that, and then it stored the memory, stored the result of a computation into the memory, or it used to use some data from the memory unit to do a computation. Okay, the second generation of computing, the first generation was vacuum tubes, second was by using transistors by William Shockley and others. They replaced the vacuum tubes with transistors which were smaller, cheaper, and less heat dissipation, which is very important aspect. And most importantly, it was a solid state device which is made of silicon. So the second generation is an integrated circuit. So again, it had a single single semiconductor die, in which, you know, the circuit was integrated in a small form factor. Okay, and the circuit was formed. Okay, the fourth generation is the VLSI, very large scale integration, wherein the a large circuit could be integrated in a small area. Okay, so microprocessor can be is called as a CPU in a single chip. Okay, some of the personal computers which came earlier was IBM PC, then Apple, and then Commodore. These were the some initial initial microprocessor based computers which came up. Okay, and then Intel also came up with some other computers. Okay, one of the first microprocessor was in 4004, which came up in 1971. Okay, so it's a basically for is like a BISCOM for business based calculator. That was the main intention. So it followed what is known as a 10 micrometer process technology. For those who are not aware of what is meant by micrometer technology, it's the smallest, smallest form factor of your the transistor that you want to have. If you look, if you're already familiar with a MOS, right? MOSFET, right? So this is the channel length of a MOSFET, 10 micrometer process. Okay, so it integrated 2300 transistors on a single chip. Okay, my integrated circuit. Okay, and it performed what is known as the clock speed of it was 400 to 800 kilohertz. It had 4-bit word size. Okay, each word was composed of 4 bits, and it was formed as a 16-bit DIP, dual inline package. And the circuit was drawn, the masks were hand cut. Okay, which is very, you can see how it was. Now it's all machine operated. So they were drawn with color pencils with one layer, one metal layer and one poly layer. Okay, the number of metal layers now is much more higher. I think around 6 or 7 layers right now. Okay, and the second generation was a follow-up of the 4004. This is 8008, in which followed up in 1972. This is also a 10 micrometer process. However, the word size was 8-bit wide. Okay, and it had 3500 transistors compared to 2300 in 4004, and its clock speed was 500 to 800 kilohertz. Okay, and again, as I said, the word size is 8-bit word size. Okay, and it had a 18-pin DIP package. 8080, this is the you can say the third microprocessor, one of the third, or you can say the follow. It went from 8-bit, 4-bit to 8-bit, and now to 16-bit address bus. Okay, so it was used in Altair Computer, which was like an early hobbyist PC, and it followed the 6 micrometer process. So now you see that 10 micrometer became now 6 micrometer, and it had 4500 transistors compared to 3500 transistors in 8008. And it now the clock speed now went into megahertz compared to 800 kilohertz. Okay, so however the word size was still, though the address bit was 16-bit, but still the word size was still 8-bit, and it was a 40-pin DIP package again, right? 8086, which is the processor that we'll be studying in this particular course, was a 16-bit processor. 19 it was for, in way back in 1978, and it was part of IBM PC. Okay, and it introduced the x86 ISA instruction set architecture, uh, by which was followed by Intel in the upcoming processors also. Okay, so they followed the same instruction set architecture. Okay, so and it used the 3 micrometer process, and it had 29 kilo, that is 29,000 transistors. Okay, and it had a speed of 5 to 10 megahertz. Okay, and the word size here now became 16-bit compared to what was 8-bit before, right? So now it became 16-bit package. However, the package is still a 40-pin DIP package, and it used what is known as microcode ROM. So what is meant by microcode is, we'll come to it in due course of time. 80286 was in 1982, 1.5 micrometer process compared to 3 micrometer process. It halved now. Okay, and 6 to 12 megahertz, slight increase in the clock speed. However, it is a 68-pin programmable gate array, PGA, and it had regular data paths and ROMs. Okay, you are familiar with what is meant by a data path after you have done the digital design course. 80386, it's a 32-bit processor. 80286 is a 16-bit processor. Okay, though it had 24-bit address lines. 80286 had 24-bit address lines. However, 80386 had 32-bit processor, which had 32-bit word size and 32-bit address lines. Okay, so it had both 1.1 micrometer process, and it had 175K transistors operating at 16 to 33 megahertz. Okay, it also had this microcode ROM, and it had a very synthesized control. Okay, 80486 is the one where the pipelining has started. Now, what is meant by pipelining? We'll see it in a due course of time to some extent. Basically, it is multiple instructions executing simultaneously, one by one. Okay, that is what I can say at this point of time. It also had floating point unit to do some floating point multiplications and floating point arithmetic, and it had a cache. Okay, which is something which is new. What is a cache? A cache is a memory which is inside the processor itself to speed up the processing. Okay, so it had a sub micrometer process, 0.6 micrometer process. Okay, and it had 168 pin PGA. So it is increasing 100 pin to 168 and so on. Okay, and then you had Pentium, which is 1993. It had 35 micrometer, 0.35 micrometer, that is 350 nanometer processor, 3.2 million transistors, 300 megahertz, and it had caches, data paths, floating point unit, control unit, and so on. It had a separate instruction and data memory. Okay, and Intel Pentium Pro 1 and 2, it was in 1995 to 1999. Okay, it was again 600 nanometer to 0.18 micrometer, and it also had 32-bit word size, right? And it performed 3 micro operations per cycle. Okay, what is again micro operations is basically, I'll tell you what is meant by micro slightly, is basically one instruction is composed of multiple small instructions which will do a small function of a larger instruction. So what is it, we'll come to it later. And then we had Pentium 4 when way back in 2001. It introduced what is known as a deep pipeline to fasten the execution of the microprocessor. It used 19 nanometer to 180 nanometer technology, and it used again 32-bit word size. And now the speed went into gigahertz. Okay, 1.4 to 3.4 gigahertz. Okay, so this is what you generally come up with, what is known as so-called Moore's law. It's not a law; it's just an observation. It says that the transistor counts will double every 18 months or so. Okay, so or every 2 years, the count doubles roughly in 2 years. So that's what it predicted. Gordon Moore predicted, and this is more or less followed to some extent, at least to the recent past. Now it is like being, it's at a difficult, with a lot of difficulty they are trying to match this Moore's law, which is like kind of a sentimental law that people want to follow it somehow. Okay, so Intel Core architecture. So you have different following up in, say, Core i7, i9 now, and 10th architecture right now, 10th generation right now. Okay, so falling to around I think a few nanometers of technology that you have, and increasing uh, the clock speed to a turbo boost around 5 gigahertz right now, right? So this is how it started. This is how the evaluation of the number of transistors from 8082 to the Pentium 4 looks like. Okay, so given that, what is actually a what is actually a microprocessor? So that's what we will be actually looking at. So microprocessor basically can be termed as this a computing device, okay, which controls different peripherals to perform a computation. Okay, the central processing unit, the CPU, where the microprocessor sits at, or is you can say is where the microprocessor sits, is actually controls your memory, which can be RAM, ROM, or different other devices, flash drives, or any other device. Okay, and it also controls the secondary memory, okay, which is his hard drive, HDD, or solid state drive, or whatever it is, and other input output devices like keyboard, display, etc. It communicates to all these peripheral devices through a address, data, or control bus. Okay, now this bus is the one on which it actually sends the data or address or some control signals. Okay, so as I said, microprocessor is a CPU, central processing unit, on a single VLSI chip. Okay, so what is VLSI? Very large scale integration. Basically, multiple millions of transistors are accommodated in a single silicon chip. Okay, integrated together to perform a particular operation, which in this case is a microprocessor. Okay, so what generally happens when you turn on your computer? Okay, so you have heard this term called as a BIOS. Okay, a basic input output system. Okay, so what is a BIOS? BIOS is basically a program which is resident on your ROM. Okay, so the ROM that you have is a small part of your memory, which is a small amount of memory, you can say that. So that stores this ROM, okay, read only memory, which is always resident on the computer. So this BIOS, which actually orchestrates the loading of the computer operating system from the hard disk drive, or your solid state drive, whichever is the secondary memory, into the RAM. So this will do the orchestration, right? And then once the operating system is loaded, okay, it operating system will now take over. Okay, so sometimes the it will also the basic input output system, also the BIOS will also coordinate the configuring or checking whether all the input output devices, they are connected to it or not, connected to the computer or not. And OS will further load the program into from the disk, that is your secondary storage, into the RAM, the primary storage. Okay, so it consists of a program. Now, what do you mean by it consists of a basic program which will actually be executed? Is the first program that has to be executed. Now, what is a program? Program is a set of instructions which is executed by the microprocessor. Okay, so these instructions will tell the microprocessor to do what operation at a given point of time. So as I was telling, so what actually the processor tells the an instruction tells to the microprocessor, it tells what kind of action it has to perform, whether it is an arithmetic operation or whether it is a logical operation or any other type of operation, which type of operation it has to perform on what is the data that it has to what is the data that has to be read from an input device if it is required. Okay, and after it performs a particular operation, it tells to whether to write into a memory or whether it should not be write to memory, or it can be used. The instruction may also tell to reset a particular system or stop a particular operation or whatever different kinds of operations that has to be performed on the computer. Okay, so basically it tells what is the action that you have to perform, right? Which can be different kinds of operations. Okay, let us say that you have an instruction ABC, add ABC. What does it say? It says that you have to perform an add instruction on three registers called A, B, and C. Now you are already familiar with what is a register. Okay, so you are already familiar with sequential registers, the shift registers, and other type of registers, right? Register is basically a place where you store some amount of data there. Okay, and that will be written or that will be read at a given point of time. So these registers, they are present inside the microprocessor itself. Okay, so I give an instruction to it in an assembly language, say add A comma B comma C. Okay, now this assembly instruction will be actually converted into a hexadecimal code, okay, or a binary code by the processor, or to tell the processor what action it has to perform. The processor will not understand an assembly instruction, but this assembly instruction that you have, which you can understand easily and write easily, so this will be converted into a binary instruction during the process of compilation. Now this binary instruction is what the processor will understand. So it will be composed of the type of instruction which I marked as red. Okay, so that will tell, that is also called as an opcode, operational code, opcode, which will tell what operation you want to perform, and followed by the other part of the instruction which tells on what it has to perform a particular operation. Okay, so the instruction will be composed of this particular opcode and other part of the code which will tell what are the on what entities, or you can say operands, you should perform a particular operation, right? Okay, now how does the once you give an instruction to a microprocessor, how does your microprocessor handle that? It fetches that particular instruction, okay, takes the instruction required from the memory, stores it in the instruction register, okay, Now, after it stores, after it fetches the instruction, then it performs the actual operation. This, you can say, this is a broad way of classifying an instruction. Okay, fetch cycle and execute cycle. Of course, there, if you go a little more detailed, you will have fetch, instruction decode, and then execute operation, then memory operation, and then write back operation, or the other way. So instruction fetch, execute, instruction decode, and then execute, and memory operation, and then write back operation. Okay, so that is a, little elaborate way of classifying an instruction. But you can say, to start with the first instance that you are right now, you are in the initial stage, so let us decode it, or let us divide it into two phases, that is a fetch cycle and an execute cycle. Okay, so before I proceed, I think I have uh, query that we have. Okay, I hope I'm audible to all of you, right? Yes, right. Okay, so fine, let's continue. I'm just
Excuse me, sir.
right. 1 second, please. Yeah. Yes.
Sir, do we need to use a specialized platform for our labs?
You'll all be told about this. You'll all be told about this. So the labs will not start tomorrow. The labs will not start tomorrow. The labs will start somewhere in February. Okay. So you will be told. You will be told about the when the labs will start at a given point of time. Okay.
Okay, sir.
Right. Right. There was one student who was trying to join. I had to answer that. Right. 1 second, please. So another thing, whenever you join your lecture, please use your BITS Gmail ID only to join. Okay. So do not use your personal Gmail ID or any other email ID to join. Okay. So otherwise, you will not be able. You will not be able to join this. Okay. So for say safety and security reasons, will be allowing only students using their BITS email ID. Okay, so just a second, the computer is hanging. Right. Uh, I'm sorry for that. It's still hanging. And about which platform that you will be using for your labs and all those things, that will be told to you. Okay, so there will be an introductory session and all those things will be done, and you will be told which platform to join, which platform to use, and all those things. So all the relevant things will be told to you, right? I'm sorry that my computer is still hanging, not responding when I try to share the thing. Are you still able to hear me? Anybody can unmute himself or herself and let me know.
Yes, sir.
Yes, sir.
Okay, I think still, anyways, it is almost time, so we will be continuing from the next class. So I think we'll call it a day today, right? it's not responding. The computer is not responding. Right. Okay. Thank you. Thanks a lot.